Good afternoon. This is Dr. Eidelberg, and today's presentation will be precision analysis of robotic system. We are in module 3, and we will open up the PDF document here of lecture 3, robot precision. The discussion this afternoon will cover a few topics. We will talk about the different sources of robot positioning errors. We look at the accuracy-related definitions, error calibration and error mapping. We'll take a look and see what they are. We'll model a position error of a robot, and we will also discuss testing of accuracy and repeatability in one dimension and 3 dimensions of robots. The positioning error types are typically classified as static errors. These are errors which are generated when the robot is moving at a very slow speed without any inertial effects. Then we have dynamic errors when the robot accelerated at high levels, and inertial force introduce vibrations in the system. So these causes dynamic errors. And then differentiations in temperature of the environment may cause thermal errors. The sources of these errors are important for an engineer to understand because the positioning error may cause catastrophic errors, including injury and damage or system downtime. They may degrade the quality of the final product. They may also cause excessive wear, and in turn will shorten the machine life. The sources of positioning error in robots may come in from joints and links. Joints, either prismatic or revolute or a combination, will cause errors such as straightness, flatness, pitch, or roll of the linear slide in a prismatic joint. And in a revolute joint, it may be the result of wobble, run out both radial and axial of the inner ring with respect to the outer ring. When both of them are active, either one of them may have friction, which may result in an error, and there may be some load variations during motions that will induce inertial forces that may also be part of this error. The links may have misalignment, they may have parallelism issues or perpendicularity, and we'll take a look at the major source of error, which is so-called AB offset. This is coming up. The dynamic sources of errors are resonant frequencies, damping, which slows down the system, and also servo bandwidth, which limits the dynamic accuracy of a system. The sources of thermal errors are thermocouple effects, constraint links. When they expand, they may not be able to move in the desired direction, and they may have also different coefficient of expansions of different robot parts, which expand in different rates, and therefore they may cause a thermocouple effect that induce an error. When we look at the Cartesian robot or a Cartesian link, we see 6 sources of errors. We see that when the slide moves in the direction, there may be error due to the measuring device, the encoder, in the direction of travel. There may be straightness error, how straight this moves, and also flatness error. And in addition, along each one of these XYZ coordinate system, there may be angular errors such as pitch, yaw, and roll. When we talk about Revolute joints, we see that sources of error may be a wobble, where the axis of the plate is not coinciding with the axis of the base. There may be run-out error when the plate comes up and down, like a flatness error, and there may be a radial run-out, such as analogous to straightness in a linear joint, which also may cause error in the system. A very important source of errors, as we mentioned earlier, is the AB offset. And the AB offset is a linear error as a result of an angular error. So see, when this slide is moving along this base, it may have pitch yaw and roll, as we saw earlier. So if you look, for example, at the roll, there may be an angular error over here in a magnitude of theta, and if the point of interest is offset by an amount which is designated here as h, we call that AB offset, then we see that the linear error, which is a result of that angular error, will be h times the angle theta in radians. Now when this is actually sine theta. H times sine theta will be the angular error, and then when theta is very small, the sine theta becomes very close in value in radians to theta. So this is the AB offset, and this is actually the major source of errors in robots. You see over here that each one of these joints of this articulating robot may have a slight error, and this slight error will have an AB offset, which includes these two links for the first joint, and will have an AB offset which includes this link for this joint, and then we'll have to add them up in order to come up with the total error. We'll see how it works over here. The schematic diagram of this articulating robot is shown here, and we see that we have a point over here, point 3, and we have a point over here, point 2, and we're interested in finding the errors based on error of each one of these angles and known length of A2 and A3. So the error at point 2, E2, is equal to A2 times the angular error of theta 2, and it will be perpendicular to the line of the link itself. So it's like theta in a z direction or in a y direction, if this is z, cross with this vector over here. And if we're looking for the error over here, then we first have to add both A2 and A3 vectorially. Worst case scenario will be when this will be in line with this guy. And then we have to multiply that times the angular error of theta 2. This will be the contribution of theta 2 to the total error of E3. And then if we add on top of it the contribution of this link to the error, then we'll come up with two sources of errors. And when we're talking about errors, we'll see in a minute about the definitions of repeatability and accuracy. Typically, the errors are of extreme importance related to the repeatability. Repeatability is a statistical error, and therefore these two errors, the contribution of theta 2 and theta 3, must be added statistically, and we'll see later that the total error is going to be the square root of the squares, sum of the squares of each one of these contributions. The ways to mitigate errors in robots could be in various procedures. One is mechanically. We could use a device such as remote compliance center, which is added to the end of arm tool, and then when we for example, require the robot to insert a pin and a peg, then in a hole, then that compliance center is going to give in the cross direction and allow the pin to slide nicely with the force, the axial force, into the hole. Another misalignment compensator, which is actually now patent pending, one of them by my name with the support of Festa Corporation, is shown over here. This is a Cartesian robot, and you see the black over here, the black element over here is a flexure done from composite material, printed composite material, one part that allows the crosslink to expand during thermal deflection, or if, for example, the two long axes are not parallel, and give while keeping the stiffness in the direction of motion very high. So these are mechanical ways of solving some of these errors. We see an example over here of an effect of a thermal load on a system. If there is a heat source on one end and another heat source on the other end, if they are not equal to each other, such as sunshine hitting the top end, then the top surface may expand further than the bottom surface, and that will cause a thermocouple effect, which in turn will cause the end of arm tool to be dislocated in this position instead of the target position. We look here at dynamic errors. We have here an example of a dispensing process where the robot is required to trace straight lines with radii, and due to flexibility within the robot, if the robot is not dynamically stiff enough, we may get a wiggling path of motion, which of course results in error. There's an error over here which is caused dynamically. And if you look at the detailed of the velocity arrow, this is a velocity axis, this is time, then we see that while we want to have a constant velocity with zero arrow, which will result in very straight line, we have here various frequencies. Now the lowest frequency typically is the bandwidth of the machine. It's the highest frequency that the machine can control with minimal error. And then on top of it, we have the higher frequencies, which are the so-called resonant frequencies that may be of various magnitudes. And we will see when we're talking about control that we need to tune the machine in order to eliminate this vibration, increase the bandwidth, reduce the overshoot, and also use some notch filters in order to eliminate some of the natural frequencies and improve the performance. When we talk about definitions of accuracy, repeatability, and resolution, this is a good way to illustrate that. We see here an example of an accurate system which is close to the bullseye. We see over here a repeatable or precise system where all the shots are very, very close to each other. And over here we see an ideal system which is both accurate and precise. The formal definition of accuracy is how close is the tested position to the target position. This is a target position, this is a test position. Repeatability, how close are repetitive tested position to each other. And resolution is the smallest value of measurable positioning change. So these are the basic definitions. And over here we see an example. We'll also do a lab experiment related to it, of how we calculate the accuracy and repeatability of a robot. So we see over here an articulating robot. Here's the tool center point, and it is programmed to move to a target position, which is right here. XR is the target position. And we run n repetitive tests, and each one of these dots represent the position where the robot ends up with at the end of the test. Now, having all these values, we could first of all calculate the average position by taking the sum of all of these positions, dividing them by the total number of tests, and this will give us the average positions. Once we know the average position, we define the average accuracy as the difference between the target position and the average position. So if the target position is farther out than the average, and we have a positive average accuracy, and if it's below, we have a negative average accuracy. The average accuracy is a parameter that can be mapped out, that can be removed from a system. We'll see how later in the presentation. The repeatability, however, is the dispersion. It's a random variable, and it cannot be improved. It's an inherent characteristic of the machine. It is measured by sigma, or the standard deviation. The way we calculate the standard deviation is by taking, for each one of these positions, we take the difference between its position and the average position. We square it. We sum them all, divide by n minus 1, the total number of positions minus 1, and we take the square root. This is the standard deviation of this dispersion. Now, we see over here a normal distribution, and if we would do many tests, all the values will actually spread out in this distribution, where we see that within plus or minus 1 sigma, there will be 68% of all the test measurements will fall in with this element. When we look at plus or minus 2 sigmas, then 95% will fall within that range. And when we look at 3 sigma, then 99.7% will fall in that range. Typically, in high-precision system, it's important to look for specification of repeatability of plus or minus 3 sigma. However, some manufacturers will not specify, and it's a good idea to ask how many sigma is the specified repeatability represent. And some, of course, will represent it as plus or minus 2 sigma. But then you can compare apples and apples of different types of robots in terms of its precision. We can map out or calibrate out the average error simply by removing it from the target position. If we, instead of commanding the robot after we know the average accuracy to go to this target position, we can command the robot to go to this target position minus the average position, and then we'll know that the average position will become 0. We see over here an example. We're not going to spend too much time here, but the idea is that we have an explicit set of 7 tests. We take the difference between it and the average that we calculated here as the sum of all of these results divided by 7. And when we add them all up and we divide by 7 minus 1, we take the square root, then we get the standard deviation. Then we have an average accuracy, which is the difference between the target position 200 and the average position, and we have the repeatability of 3 sigma, which is 3 times this value plus or minus, and we have the total accuracy, which is the sum, the absolute maximum sum of the average accuracy plus the repeatability. So if you want to calibrate the average accuracy out, you see that a simple program that's sending the robot to position 100 several times. Once we know the average accuracy, we can send the robot instead to 100 to 100 plus the average accuracy, and then we will eliminate very closely the average accuracy. when we send the robot along a straight line rather to a single point, then we can use laser interferometer, typically used in order to measure the position of the robot along its path of motion, and we can send the robot along the blue line and then come back, and over here for each one of these paths we could measure the error, the position error, and we come up with a chart like that. And in a chart like this, we define the repeatability as the largest gap within that travel. This is the total indicator repeatability error, and if we look at the maximum minus the minimum error, this gives us the maximum accuracy of the robot based on this test. The mean or the average of each one along each one of these lines is the average accuracy. So this is the average accuracy. This is the total repeatability, and we could either specify total repeatability as total indicated error from here to here, or plus or minus, which is going to be halfway to the average. So these are the basic definitions, and we could see here that we could use these information in order to do two endpoint calibration for this particular path. So if we know the total accuracy and we know the travel, we can calculate the slope of accuracy divided by the travel, and then if we multiply the slope times each one of the positions that we send the robot to, we can deduct from it the portion which is relative to the slope of that line, and in that way we will remove the average accuracy. So if the average accuracy was previously like that, after two endpoint calibration, the average accuracy will be here. We remove this linear error out of the positioning system, and we end up with this curve. You see still that we have these little waviness, which if we want to get rid of that, we need to do mapping. So the way we do error mapping is by measuring the waviness at very small intervals, and then adding a map into the positioning system. And when the controller sees that we send in the robot to a certain position here, it goes to the map and see what is the error, and then it removes that error, and what we see at the end is that the average error after error mapping is a straight line at a value of very, very close to zero. However, we cannot get rid of the repeatability, which is exactly what it was to start with. To take a look at a typical system test of repeatability, which we'll be doing in the lab experiment. You can click that link and it will show you how it is being done. Again, we will do this at the lab experiment, and this is the final slide that shows us how we do three-dimensional error mapping of a robot, or doing dynamic tracking. We have a laser interferometer, which is controlled by the PC over here or laptop, and this laser actually is shooting into the robot. The robot sensor traces it, and it transmits back the precision to the host computer. So this completes our presentations of robot precision, and we'll practice more of it in exercises in lab experiment. Thank you.